the bell work for us. Yeah, this grocery store sells a bag of 7 oranges for $4.48. But you got $6.40 to spend on oranges. How many did you buy? So this is a proportional type problem. Here, so I'm going to set up a proportion, 2 fraction lines, and an equal sign. You see the 2 labels we have here are oranges and dollars. Okay, so my first label here is oranges. I'll just put that in the numerator, although it doesn't really matter where you put it. But I will say that for the most part, when people have dollars as one of the labels, they'll usually put that in the numerator. But for our purposes right now, this doesn't really matter. If you're finding a unit rate, then that would matter. Okay, but the other label there is dollars, so we'll just put that into the denominator since we've already labeled our numerators with oranges. Okay? All right, from this though, it says up here at the top, 7 oranges for $4.48. So in my first fraction, I know the number of oranges there is 7, and the dollars there is $4.48. Okay? But then it says you spend $6.40. So that's a dollar amount that I know right there, $6.40. We just don't know how many oranges that's going to be, so I'm going to put an X there. You just leave it blank or put a question mark if you'd like. But now that I have my proportion set up, I'm ready to solve it with fish method. Okay. But if you like cross multiplication or any of the other methods, then feel free to do it. Just for me, this is what I'm going to use. So remember, you always start with the unknown, like this, in this case, X. I make the tail of the fish, so I go straight down in this case. And the first number I encounter there is 640. I cross up to the top, making kind of the body of the fish. There's the 7s next. And then when I swing this back around, I get the head of the fish at $4.48, and then I end where I start, which should be wherever the letter is for me, which is just X. So this gives me something that I can just type into the calculator, 6.40 times 7 divided by 4.48, enter, and I get 10. Okay, now, again, this is X, but we don't really need to write X as part of the answer because I put that X in there, but it's 10 oranges. This is a word problem, so make sure that you label that. There's our final answer there. Today we are starting a new unit, Unit 10, and for the most part, there's one lesson that will kind of do a little bit with the proportion stuff, but for the most part, we're really looking at shapes. So you could call this kind of the beginning geometry unit. I don't really care what you call it, but Unit 10. Okay, so here's our 2 objectives for the first lesson. I know what vertical, complementary, and supplementary angles are. And the second objective, I can solve for missing angles and values with vertical, complementary, and supplementary angles. Take a minute, copy this down, and we'll get started. What you'll notice about this objective, both of these objectives, that we see maybe some new vocabulary for us. Vertical, complementary, and supplementary angles. These are types of angles. And if you don't know what an angle is, that's okay. We're going to talk about that too. But this unit is very vocabulary heavy with words like these. Okay, but as long as we understand what they mean, which hopefully you will, especially after the lesson and the assignment, then we see it's not really a big problem. But we have to get past this language barrier because if we don't understand this stuff, then it can be more difficult than it needs to be. So lines, for example, we'll see lines, but lines can also be, there's also different types of lines, I should say, rays and segments. So it's lines are the ones that we're going to be looking at. They're usually straight and they're connected between or through 2 points. Okay. Now the thing is if they're connected between 2 points. So let's look at that. That's what we call line segment right there. So if I have a point right here and a point right there, and I can connect those two with a segment, with the line, I guess again we'd call that a line segment. Okay, because this line segment right here that I've drawn has ends to the line. Okay. In fact, I'll put that in here. Now, in terms of naming these as well, which is going to be important for us, I'm going to just label the 2 endpoints A and B right here. Now, they may show a line segment like this. AB with a line over it. Now, that may not look so fantastic, but the order of the letters makes a difference. If I write this as line AB right here, this tells me that I'm going from A to B. See that? I could also name this if I wanted to. Not that I know that anyone would want to, but you could name it BA like this, okay? But again, that indicates that the line is going, I guess, backwards for me from right to left. So order does matter for the letters, okay? Now, something, because this is new for us, you may have noticed there's not any arrows on either of these two lines that are above the letters. That is how we know it is a line segment and not a regular line, or what we're going to see next as a ray. Okay? But usually we'll use at least 2 points. It is possible for a line segment, I suppose. You could say that there's a third point in there, and then you could call it ACB, but we're gonna skip that for now. Okay, so just look for 2 letters. Array, on the other hand. Okay, so array, it's still a line, but it goes through 1 point forever. Yeah, that's it. Oh, if I can spell forever right. Line that goes through 1 point forever. Okay, but it has to start at another point. So maybe I should have put that in there, but technology. So let's put 2 points down here. Okay, so I got this point right here. I'll do it the other direction. I'll put this one here and this one. Okay. Now again, we should connect these 2 points. Okay, but I would have to show that this line is going to go through one of these points forever. So I choose this one on the right, and generally speaking, they will put an arrow at the end of the edge of one of the lines. Okay, but again, we notice that it starts here at this point, so let's put labels on these ones. Okay, so I'm going to put different labels. We'll just say C and D. You can use whatever letters you want, but this would be considered ray CD. Okay, so we show this way, CD, and then we would show the arrow this way. Okay, but again, the difference between these two, the CD here now has an arrow, whereas AB and BA did not. Also, the direction, remember the direction is important, or the order of the letters is important. So I would not put, this is what I would not want to put, this would be incorrect. This is not ray DC this way. It is not that, because that would indicate you start at D and then go through C forever. But this line does not, this ray does not, okay? All right, so line segments, again, 2 ends. Array has essentially 1 end, and then it goes forever in one direction. And then we have a line which goes forever in both directions. I'll say 2 directions, but you can put whatever you want right there. So this is a line, okay? But again, let's give ourselves a couple points here. So there's a couple. That seems okay to me. And we'll just connect them, something like this. Quite horizontal, this line. But if this is a line, generally speaking, we'll put arrows at the end to indicate that it goes on forever. Okay, so let's put some labels on these. We did C and D, so E and F on this one, okay? So we could say line EF right here, but again, we'll put 2 arrows at the end there. And again, even though this goes forever in the leftward direction, the direction you could say is important. I'm starting from the left and going to the right. That's what this says. At least the way that I have it written, EF right there. If for some reason you were like, hey, I want to go from right to left, well, then you'd label it FE. Again, you'd have the line above it, but now it's got the 2 arrows, okay? Now, so we got line segments, rays, and lines. Generally speaking, we tend to interchange these. So sometimes we'll say line segment, but we mean line. Or we may say we have a line, but we actually have a ray. And so depending on how math nerdy you want to be about this stuff is up to you. Okay, but we may be seeing some of these, and so I may be using some of this vocabulary here. And it's important for you to understand what I'm saying if we're using it in a math context, okay? Now, along these lines, we have what we call a vertex. If you have any one of these types of lines, line segments, lines, or rays, the intersection point of either one of these, and it could be mixed, is called a vertex. Why don't we just call it an intersection? I don't know. Freaking math nerds, okay? But yeah, it's an intersection point. If you want to just call it that, that's fine, but I will be using this vocabulary vertex fairly often in this unit, okay? So let's go and take a couple lines. I'll make them line segments just because it's going to be easy for me. So let's take this line segment and this line segment right here. I'll use a different color. Boom. Okay, so these two line segments, which I will not name, this point of intersection right here in orange, that is the vertex, okay? By the way, sometimes I think math people, we do this, if I haven't said this already, we do this often, we change vocabulary words to make us look smarter than we are. Because I think some of you guys have noticed that math really isn't that hard, but we make it hard by changing vocabulary words and stuff like this. But this is a vertex. Usually a vertex will be associated with some kind of letter, like any letter, T. V seems appropriate. It's a vertex V right there. V for vertex. It's not always going to be a V. I just used V because it seemed appropriate. And maybe that kind of looks like a Y, but whatever. Doesn't matter. Okay, but a vertex is an intersection between two lines, rays, or segments, or again, but it could be a mix. Like this purple line, if I wanted to make it a ray, I could put an arrow on one of those. Now I have a segment and a ray that intersect. Doesn't matter. We still have a vertex. Angle. So we saw on the objective that we do have what we call angles. Okay, an angle is just a space created by two intersecting lines. When I say lines, they could be rays or they could be segments. It doesn't really matter. Okay, but it's space created by them. And so you're going to have two lines, whether those are rays or segments or just regular lines, and then you'll have a vertex. So they need a vertex, right? An intersection here, okay? So let's take, I'm going to take two rays. We'll make this, I'll use some technology to make this pretty. So we got this ray right here. And let's get this ray right here, okay? And we'll pretend like they intersect right there. Okay, so let's give ourselves a nice vertex. And I will label it again V for vertex, although you could label it whatever letter you want. And then we got this ray in purple, and then I got this ray in blue right here, okay? So there's a space created by these two intersecting rays in this case, which is the angle, okay? Now the space that we're talking about specifically is the space between the lines. So I'm looking at, and I've purposely given this green marking an arch to show that this space right here is the angle. Okay, now this is a pretty thin angle right here. Like if this were, I don't know, like a pencil would say, that's a pretty sharp pencil right there, right? But they don't always have to be that sharp, I guess we could say. You could, if you wanted to, make it not as sharp, right? So we have this line right here, this line segment, and maybe this line segment, okay? Okay. Again, not sharp, not so sharp, and I can move this as I go, right? Make it not very sharp at all until it's just kind of straight line, right? Very flat, right? I'll emphasize that this is an angle though, so I'll give it some angle lability or licity. But this right here, again, is what we consider an angle. Okay? Angles are measured in degrees. So that's how we define the space created by these lines, rays, or segments, is with degrees, okay? I don't think we'll get into those specifics, but you're welcome to Google it at home if you're really interested in this nerdy crap, which unfortunately I am. But angles can be named in three different ways. Sometimes they're named by the vertex. So let's come back here. I'll put this one in as V for vertex. So we could say, for example, this one right here, this would be considered angle V. Okay, so that's just naming it by the vertex. sometimes they'll use letters, I guess, so labeling the angle with a letter, which is, I guess, what they've done. Sometimes what they'll do is they'll just throw a number in there. They'll say, this is angle 4, okay? And so they'd say, again, another way to label this one, this particular angle would be angle 4. So sometimes it's numeric, and I'm still pretty much labeling it by the vertex. The problem with this is if you have actual lines that go through the vertex, then it's like, what the crap angle are we really talking about? Let me demonstrate this, maybe. So let's look over here on this one on the right. If I were to extend those lines, and let's pretend like I drew good lines, like this, right? If I said, hey, let's look at angle V, it's like, which one are we talking about? This one in green, this one, or this one? I don't know. So that's where labeling it with this third method becomes, I think, pretty nice, because we can label it with 3 points. For example, again, I'm looking at the diagram on the right. Let's make this point TUV. So we'll make this one a U right here. That's a U. So we could label this. If I wanted to acknowledge that green angle that I've already marked on the right here, we would name it. Angle TVU. Okay. And again, the three points just tell us where to go. Again, starting with T, I would go to V, and then U, which creates this green angle, which we've already marked. Well, what if I wanted to name it because, you know, angle UVT. Just like we saw with the straight lines, this is exactly the same angle, it's just the direction is different. Okay, so when you see lines going through the vertex like this, I say it's pretty crucial to name it with 3 letters like this, but we won't see that on the assignment. Just expect it in the future though. Okay, now, up here at the top, we see this marking right here. That is the angle mark. It's the symbol, I should say, the symbol for angles. Okay, why do we have a symbol for angles? Because math people are lazy, and we don't want to write the word angle all the time. So we use a symbol for that, just like if we went back far enough. Instead of saying add, we use this symbol right here, right? Now we're using a symbol because we're going to say the word angle so often and use it. We're just going to use this right here. So, for example, angle V, I could have just said, hey, look, angle V, angle V. Now, I put this mark through it right here. Not everyone does, but you're welcome to. Or if I wanted to label it angle 4, angle 4. Okay, that's fine. It just kind of looks like a less than symbol if I do it, so I like to put the mark through there. What about these other two that we did? Angle TVU, so that'd be angle TVU. Or if I wanted angle, for some reason, UVT. There we go. All right. Now, I'm pointing out all 3 ways to name angles because we may see them on the assignment, although they don't, if I remember right, again, we won't see the 3 points, but it's very appropriate to use that method. If you just walked in right now, you'd be like, this looks like some kind of foreign language, which it is, kind of, right? We're using our own symbols to represent words now, which is when mathematics really shows that it is a form of hieroglyphics if we're going to use the symbols like this, okay? All right, so if there's no questions for the angle stuff, down here we see what a word we call congruent. And there's a symbol for that right here. It's an equal sign with, I say it's the Enye symbol. But I don't know what it's formally called, this little wavy line right there. But this is the congruence symbol right there. So, again, just in the future, if you see this symbol, it reads congruent. So I could say, for example, in the future, we may say angle J is congruent to angle B. All right. Congruent indicates that the 2 shapes are the same. And in this case, the shapes we're talking about are angles. Angles can be congruent. They're the same. Okay. It'd be hard to demonstrate that even, well, maybe with not so much with technology. So if I said, here's angle J, and I wanted angle B to be congruent, boom, there you go, copy and paste, right? So this one right here we'll say is J and this one's B. Same exact angles, which means we would say that they are congruent. All right, now we're into more objective stuff. Okay, vertical angles. Angles opposite to each other through the vertex. So let's give ourselves two, I'll make them lines, what the heck. So here's a line right here, and let's give ourselves another line right here, okay? Again, I'll say that the intersection here is a vertex. So if we look at vertical angles would be such like this one right here and this one. Okay, let's give ourselves some points so we can label these as well. You know, these other points right here, A, B, I do better B than that usually, C, and then D, okay? So the angles that I've just marked right there would be angle I'll say AVD. Some of you may have said DVA, and that's fine. And then the other angle I have marked as angle BVC. But again, if you put CVB, that's fine. Okay, these are what we call vertical angles. Okay. Now, these two vertical angles are opposite through each other through the vertex. To each other through the vertex. And this is what I mean by opposite to each other, this way. But there's also two other angles that are vertical to each other, which would be, I'll still use green here, AVB and DVC. Kind of lighten the green there, hopefully that helps. Because they are also through the vertex, it's just an up and down relationship through the vertex. See this? So again, I'll specify this. Angle AVB and angle DVC, these also are vertical angles. All right, vertical angles create a special angle relationship. For example, angle AVD and BVC, see these are through the vertex, but the angle, the space created by these two lines, I said I'd make them lines, didn't I? Now they're lines. There we go. Okay, so these two lines create this intersection, but what you may have noticed is that if I were to connect these this way, and if my drawing skills were better, and I connected BVC this way, these angles are exactly the same. Okay, so this is where we run into congruence. Remember I said, I'm not going to write the word out either because congruence is a long word for me. I'm just going to use a symbol. Okay, these vertical angles, AVD and BVC, are exactly the same. They are congruent. Same with angle AVB and DVC. These also are congruent. As it turns out, vertical angles will always be congruent. And I spelled the word there because I was typing it. Always. They will always be congruent. Find the measure of the missing angles. Well, what's the relationship between these angles? That's a good question right there. What is the relationship with these two angles? I think some of you guys noticed, just because we went over the vocabulary there, 57 degrees and angle B right here, they are through the vertex. So these two are vertical. Okay, well, since they're vertical angles, that means that these two angles are congruent. All right, well, maybe we've forgotten what congruent means. This means that they are exactly the same. So in other words, if this angle right here is 57 degrees, its vertical angle will also be, you guessed it, 57 degrees. Boom, vertical angles. But that is the thing about problems like this one. This is angle B right here, so I do need to label it in degrees. And this is, I guess I may have missed that, but this is the marking for degrees. It looks like a little exponent that's 0. It's not. It's just a circle 4 degrees right there. Well, what the crap is this? One of the angles is shown as a expression, some kind of math expression right there. But Again, we see the vertex right here, the intersection of the two lines, and we got this angle at 118 degrees, and then this one at 6s minus 8 degrees for some reason. But we see that these two angles are vertical because they are through the vertex, opposite through the vertex. Well, since they're congruent though, these angles are congruent, these angles are vertical. Which means that what I can do out of this information that I have so far is to write an equation, right? This means I know that the 118 degree angle is exactly the same as the 6s minus 8 degree angle, meaning they are equal. Now, notice I'm saying they're equal because they're congruent. I don't really need the congruent symbol because I've just made an equation out of this. And the great thing about equations is we've already learned how to solve these, so I will. So isolating the s's, I would add 8 to both sides. Make that 126 looks like, which now equals, I'll drop the 6s. Isolating them, just as planned, zeroing out those at minus 8. And then the last thing here is to divide both sides by 6 to make it 1s. Okay? So in my calculator, I go to and put in 126 divided by 6 to get 21. Now, this is just a value for s. This is not the actual degree. We know that this angle is 118 degrees. So I'm not actually labeling this with degrees, okay? Well, those are vertical angles. Okay, so that kind of satisfies both objectives for vertical angles, but now we have what we call complementary angles. Complementary, that's when two or more angles add up to 90 degrees exactly. And a right angle, right here, that's a 90 degree angle. Okay, so that's sometimes they'll say it's 90 degrees. They just make a 90 degree angle altogether. Generally speaking, we will not be looking at more than two angles, but as long as we understand we're looking at two angles, okay? Well, what does a 90 degree angle look like? Here we go with my artistic abilities, but here's a line right here. And here's the line right here, okay? And of course, we have the vertex. These are two rays, I guess I should say. We've got the vertex. Generally speaking, they will use a marking to show 90 degrees generally. And it looks like this. Again, it may not look exactly like that on the assignment because my drawings suck, but this is a 90 degree angle, a right angle. Remember that angle mark, so I don't want to write the word angle. So these are right angles. Well, what I'm saying here is that this would be one angle. So we wouldn't say that it's necessarily complementary. It's just a right angle. But if for some reason I were to split this up this way, that's a better line, I guess. Then we would say we have two angles. This one right here in red. And I'll make this one blue. This one right here in blue. Okay, this red angle and this blue angle combined would be this 90 degree angle. So that would make these two angles, red and blue, complementary angles, okay? And again, you could split this up into 5 or 6 or more angles, however many you want, but we should only be looking at two together. But again, you have to understand that these add up to 90 degrees because eventually we're gonna make equations out of this. You got a 90 degree angle equals red angle plus the blue angle, okay? Whatever these are, and they may be numeric, they may be expressions, who knows? Or they may even say, look, we don't know what the red one is, but we know the blue one is, so figure that out. But we should be able to do that. There we go, find the measure of this missing angle. Okay, so they've even given us a little 90 degree marking right there. And one of these angles right here, 36 degrees. We just don't know what the crap this one is, okay? But here's what I do know. I got this, I'll say this is my red angle at 36 degrees. And then I got this other angle A, which I'll put right here. In fact, I'll say it's angle A. Well, I know these two angles make up the 90 degree angle, which means if I add them together, I should get 90 degrees, boom. Okay, here's an equation. And I have seen some students, instead of using angle A, they'd use an X right there. I'm gonna keep it as angle A so I know that I'm actually solving for angle A right there. But there's an equation that we need to solve. Hey, no problem. Just one principle of equality should do it by subtracting 36 from both sides. Okay, so 90 minus 36, 60, 54. And yeah, 36 zeroed out, which means that my angle A right here, I can just drop it. Now, if angle A was an expression, which I think we will see, I'd need more work there, but that's it. 54. In fact, this one is an angle, right? So I should label it in degrees. 54 degrees is angle A. Well, that's messed up, man, but is there a way to check? Yeah, there is. What is 36 and 54 if I add these two together? Because that's what I'm saying right here, this is 54 degrees. Well, if I add these together, I do get 90 degrees. 36 plus 54 is 90 degrees, as planned, because it told us it was 90 degrees. I think you guys see that we're solving with some equations right here, right? And it's so fun. So, this one right here, again, there's our 90-degree angle mark, meaning that these two angles are complementary. And what do we got? Well, I got angle A right here. That's an A. And then I got the 73-degree angle right here. This means if I were to add these together, I'd get a 90-degree angle. Which again, it's showing right here. That's how we know that it's going to be 90 degrees. Okay? So they are complementary angles. I should probably write that. I forgot to do it. Complementary angles. Meaning they add up to 90 degrees. Okay, well, this is an equation that we can solve. No problem. One principle of equality should do it. If I just zero out that 73 right there. So minus 73. If I do it to one side, I got to do it to both sides. Okay. So this tells me what angle A will be because 73 minus 73, it's 0 just as we planned. 90 minus 73 though should be 17. And this is the actual angle, so I'm going to put degrees on that. There it is. Is there a way to check? Sure, just like we would an equation, right? Remember you could say, well, angle A is supposed to be 17, right? 17 plus 73, does it equal 90? Sure it does. That gives us a true statement. And here we see already, just based on the last three examples that we've done, including this one, that solving equations, principles of equality, yeah, it's pretty crucial stuff, or at least we use it often. Crucial or not. What you're describing there is a shortcut. I'm kind of avoiding the shortcut because I was told to avoid it by an unseen force. But I'm talking about the math department, you guys. Yeah, some students are like, I know this is a complementary relationship, so I know I can just take 90 and minus 73. Yeah, it still works. All right, so here we see this one right here, this angle, is it's an expression. Okay, now we can solve for it the same way that we would, like I was saying on that last one, you could say, I know it's 90 minus 33, but that's just this angle. It's telling us to solve for y, not just the angle right here. So remember, y is not a degrees. It's part of an angle in degrees, but not the actual value of the angle. So there's no need to label our answer when we get there, okay? But again, I see the marking here for 90 degrees. So I know it's 90 degrees. It's going to be the same as this 33-degree angle. So it's going to equal the 33-degree angle and then this other angle right here, which is an expression, 2y plus 1, okay? So 2y plus 1. Some people put that in parentheses, but I have that color-coded, so I'm not going to do that. But it's plus, okay? Well, now it's a multi-step equation that we need to solve, which we have seen, and we pretended to enjoy. But principles of equality, not yet, not yet. We would look for distribution first, which this does not have any, but it does have combining like terms, the 33 and 1. If I add those together, I get 34, okay? Now I still got my 2y there, and it's still being added to the 34. This should still equal my 90. So let's solve for that 90 then. So I will get rid of that 34, and by get rid of, I mean zero out. So minus 34. This is now a principle of equality, though, so if I do it to one side, I need to do it to the other side as well. So this looks like it's going to be 56, which equals 2y. 56 equals 2y. I don't want 2 y's. I want 1 y. Right? So another principle of equality will do this to make this 1y just divided by 2. Okay, so I'll show the division a little bit different this time. But that appears to be 28. Again, I don't need to label this in degrees. That should do. Can we check to make sure this works? Sure. 2 times 28 is 56. 56 plus 1 is 57, plus the 33, boom, 90, exactly as planned. We did it. That's 2 parts of our objective for the day, right? We need to be able to solve for and solve with supplementary and vertical angles. The last one we saw on the objective was supplementary angles. When 2 or more angles add up to 180 degrees exactly. Now, the thing about 180 degree angles, and I think some of you probably already knew this, it makes a straight line. Okay, so and I was kind of demonstrating that earlier when we were looking at angles. So let's look at this right here. Okay, so I'm going to give myself a straight line, and I'll make it an actual line by putting some arrows at the end there. It's not a ray, it's not a segment, it's an actual line right here, okay? Now, if I put a point right here in the middle, we could say that we're looking now at 2 rays, right? But this could be my vertex. But this is still an angle. It's just a straight line angle, okay? And that's what we call 180 degrees right there, okay? So that's what we mean by 180 degrees. If you were to cut this exactly in half, of course, 180 divided by 2, well, that'd be 90 degrees, right? So you'd end up with, something like this. And the truth is you could, right? You could say, look at this angle, 180 degrees right there that I just drew, and we'll pretend like I have good drawings right here. But now I got this angle right here, and I got this angle right here. In fact, I said it was split exactly in half, so that's 90 degrees, and that's 90 degrees right there, right? So as long as we see here 90 degrees, and this one's 90 degrees, these 2 90-degree angles add up to 180 degrees, which makes these 2 that I've just drawn out supplementary, okay? Now, they're not always going to be split in 90 degrees, of course. Okay, it's possible you could have a straight line like this one, and it could be split this way. Okay, now it's not 90 degrees here or here. Okay, but those 2 angles nonetheless are supplementary. So it does say that it could be split up between more angles, but we should only be seeing 2 again on this. Okay. Now we have what we call adjacent angles, which for now we're pretty much looking only with supplementary type angles. But they're just angles they share a vertex and one line, okay? All this is saying is that they're angles that are next to each other, okay? But again, they have to be next to each, there we go. They have to be on the same line, all right? So you wouldn't say, like these 2 angles, the one in red right there, hey, I got this angle right here, they're next to each other, so these 2 are adjacent. No, that's garbage. They actually have to share a line. So, we could have a line like this one right here. And again, it is a line. You could have 2 adjacent angles like this one and this one. Okay, those 2 are adjacent. Now, if there's more splitting up on this, so let's say we have another, we'll say a ray coming through out of that vertex. Then you'd have the orange and green these 2 are adjacent, but it's possible you could have this other third angle right here. It's just now the red one is not adjacent to orange. See this? Red is adjacent to green, green is adjacent to red, but not red to orange, okay? Because they're not next to each other. They have to be right next to each other. Share the vertex and one line. See how red and orange right there, I guess they share this line right here, but again, I'd be saying that you got 1 ray, 2, 3, 4 rays right there, okay? So they just need to be right next to each other. Now I bring up the adjacent thing because supplementary angles generally are adjacent, but also the complementary ones that we saw as well were considered adjacent. So remember the complementary angles, it's a 90 degrees right here. We'll pretend like I drew a nice angle right there. If I split this up like this, we got this red angle and this orange one. Those 2 are still adjacent, okay? They share this ray and the vertex. So, generally speaking, we will use some kind of equation to solve these, all right? But the first thing I would see out of this one when I look at it here, I look at angle B and angle C right here, okay? So we got angle B here. Again, I'm just looking at it. Angle B and angle C, they're through the vertex, so I know they're vertical angles, okay? Meaning, again, they are congruent or the same, okay? It's just, I don't know what either one of them are, so I've got to use a 63-degree angle. I would probably use B right here. What I notice about B and the 63-degree angle is that it creates this straight line. Again, you can call it two rays if you'd like, with the vertex in between. But I noticed this as well. Angle B and the 63-degree angle are supplementary. Okay, so again, that means they add up to 180 degrees. Okay, well, with that information, I can solve for B. And you could say, see this line right here? C and the 63-degree angle, they're supplementary as well, which is another reason why B and C are congruent. Not that I think you care. In any case, I'm going to write an equation, meaning my 63-degree angle, and I'm using angle B. If I were to add these together, I'd get 180 degrees. Supplementary, okay? Now, the way that I remember that angles are supplementary, just the vocabulary there is, it starts with an S, and it creates a straight line. S for straight line, S for supplementary, 180 degrees. You have to memorize the 180-degree thing right there. All right, well, now that I have this, I'm ready to solve. So I'm going to solve for angle B. So I got to zero out the 63, so minus 63 from both sides. It's going to zero that out. I can drop angle B now, which equals 180 minus 63, 117. Now that is an actual angle right there, so I have 117 degrees. But, like we said in the beginning, angle B and C are vertical, so they're congruent, they're the same, meaning that angle C also is going to equal 117 degrees. I did it. Most of the time, students just know 180 minus 63. They don't actually make the equation right here. But once we start seeing maybe B and C be some kind of expressions, then generally speaking, I'll see more equations being used. But it's up to you. Okay, oh, here we go. So right here, I see 61 degrees and angle A. These are adjacent, okay? Now, adjacence here doesn't really matter. In fact, most of the time it won't. The two angles are adjacent. Adjacent. Yeah, something like that. But again, most of the time this has no meaning. What we really need to notice right here is that the two angles are going to make this straight line, right? This one. Right here. Which means that the two angles are supplementary. That's the more important thing right here. Which again, supplementary means they add up to 180 degrees. Okay, and this allows us to make an equation with this, right? We got the angle A, and we got the 61-degree angle, right? They make the straight line. So that means if I were to add these together, then I'd get 180 degrees. Well, this is a pretty easy equation to solve. Again, I think some of you guys would even skip this step, which is fine if you do, as long as you get the same answer right there. I want to zero out that 61 so that I can just drop my angle A right here, which is what I'm solving for. So that's what I'm going to do, minus 61 from both sides. So this one, 119, looks like. And again, it's the actual angle right there, so it's 119 degrees. I only had to solve for one angle right here. No problem. Again, right here, if by chance the line, this ray right here were to extend to make it a line, then I would know that this angle right here would also have been 119 degrees. Or if they gave us, if they wanted us to find this one, we'd know that one's 61 degrees, okay? And that's from vertical angles that we would know that. All right, here we go. This one, we have two lines, right? That are intersecting right here, this vertex. But we got this angle right here, 107 degrees. And we got this one right here, 8V plus 3. But we notice again that they create this straight line right here, which means that they add up to 180 degrees. So let's go and write this out, right? Got 107 degrees. And then I got 8V plus 3 degrees. Those are the two angles. If I were to add them together, I'd get that, not 90, 180 degree angle, which is just a straight line. But now that I have this, I'm ready to solve for V, which again, V is not an angle, it's just a letter in part of the expression 8V plus 3. So, first thing here, actually, not principles of equality, right? I can combine some like terms, 107 and 3. Very long, but yeah, 107 plus 3 is 110. Thank you. Now, again, the process is still the same. Still add the 8V, just make sure you're adding those right. So that's going to be 180. Well, principles of equality. So right here, I'd say let's get rid of the 110, zeroing it out. So minus 110 there. It's going to make that 70 now. And that allows me to drop the 8V because we zeroed out the 110s, right? So 70 equals 8V. And now, yeah, we'll divide both sides by 8. It is still a principle of equality. So there we go, divide by 8. Which I already did in the calculator. Because it was so fun. And as a fraction, it gave me 55/4. As the decimal was 13.75, but it's still 1V, which is exactly what we wanted. Okay. As much fun as that was, that ends the lesson. There's our two objectives. I know what vertical, complementary, and supplementary angles are. And then, just like we saw these last examples, I can solve for missing angles and values with vertical, complementary, and supplementary angles. Hope you guys feel pretty good about that stuff because we're going to do the assignment.